Welcome. In this video, we're going to start talking about mechanical vibrations. Ooh, that is very thick. We're going to start talking about mechanical vibrations. And we're going to start with sort of the simplest case of that, which is free undamped motion. A couple warnings about this in comparison to the lecture notes. So this is going to differ kind of a lot, but also like not that much from the lecture notes. There's two reasons for that. The first is that there's a typo in the lecture notes, which I'll speak about a little bit later. And the second thing is that they use a different convention than I'm going to use. And my main reason for doing that is because the convention I'm going to use is going to be the same as the convention used on the web work. Right, so we're going to start off our discussion by just mentioning Hooke's law. So this is a law in physics about springs, and what it says is the force exerted by a spring is proportional to the displacement of of the spring from its rest state. All right, so to get an idea of what it's talking about, let's sort of imagine a spring. And we will sort of imagine that this is its rest state right here. So we'll call this 0, displacement 0. Now if I stretch it out, if I pull on it downwards, and here's sort of the first part where I'm going to differ. So we're going to use the convention that's kind of opposite to what might be you use most of the time, but I think it's pretty convenient for problems like this. So if we pull it down, this is going to be positive displacement. And let's say this is, positive displacement D. Okay, then if we, if we're pulling on it down, then there's going to be a force vector, going up that has to cancel out our force down. And similarly, if we sort of push it in, so if we squeeze it so it gets all the way up here, then the spring is going to want to expand, and we're going to get a positive, or we're going to get, a positive force vector going down. So, right, this is sort of backwards, but up direction is going to be negative, and down direction is going to be positive. And so what Hooke's law says is that f of s, and so if this is negative displacement, we'll say negative d up there. Is that there's some constant k that's going to depend on the spring And then the force is going to be, negative k times d. D is our displacement. Note, it always has to sort of be the opposite sign of the displacement. And so k has to be greater than 0. So the two changes I guess I'll point out is, first of all, in the lecture notes it has just equals k here, and I believe that that's just wrong. That doesn't matter. That has nothing to do with us changing the convention for positive versus negative displacement. If Fs is the force exerted by the spring, then it needs to be negative k. And then the second change was we're using positive displacement to mean displacement down. Okay. So sort of continuing with this. So, suppose we attach an object of mass m to a spring. And we're going to let y denote the displacement of our object from its rest state. So what that means is when y equals 0, this doesn't mean that the spring, this isn't like the natural resting spot of the spring. It means it's the natural resting spot of the spring with the weight attached. Okay. So if we have this, let's think about what this means. Okay, so y here is essentially our displacement. So we're going to end up with f of s equals negative k times y. However, remember also that force equals mass times acceleration. And so we can sort of use this formula and say, well, we have a mass of m. We're sort of assuming here that the spring has negligible mass, which we're going to do for all of these problems. So f of s is equal to m for our mass times our acceleration, which we can measure with the second derivative of displacement. So what we get is a differential equation which essentially models Hooke's law, which says that our mass times our second derivative is equal to negative k times y. And if we just move that over to the other side to get something a little bit more familiar, we get something like this, where note m and k are both strictly positive. So since we can sort of model this via a differential equation, we're going to go ahead, continue down, and end up solving this differential equation. Before we do that, though, let's focus on one part. So m, right, mass, we're going to be given for most problems because we could always measure, how big something is. K is a little bit weirder. So K is going to depend on our spring itself. And we're going to need to sort of do some measuring of that. So let's look at an example to see how we might compute K in practice. So a 2 kilogram mass is attached to a spring stretching at 8 centimeters. And we're just asked, what is the spring constant K for this system? All right, so a couple things to point out. It's a little bit vague exactly what this means, but I'm just going to tell you this is sort of a convention in these sorts of problems. When we say it sort of stretches it 8 centimeters, we're going to assume that the new equilibrium position is where that's being measured to. So if we put it on, let it go up and down, boom, boom, boom. 8 centimeters is exactly how far it would go sort of when it sort of comes to a rest. So this is new equilibrium position. And that's going to sort of be the case in all of the examples we do and the examples on the web work. Okay, so let's think about this a little bit. So we have sort of two different forces acting on us here. So if we draw sort of a picture, here's our spring with nothing attached, and here is our spring with something attached. We know that this is 8 centimeters, and we also have sort of the following force diagram, right? So we have a force going down due to gravity, and we have a force going up, which is being exerted by the spring. Right, and this is our new equilibrium position. So really what that says is Fs plus Fg is equal to 0. So Fs we can compute, at least in terms of K. Fs is negative K times our displacement of 8 centimeters. Now, I'm going to hold off on that. For our FG, we have a 2 kilogram mass. This is force due to gravity, right? So that's just mass times our gravitational constant. So we got 2 kilograms. And then if we want to use a thing for G, we're going to do positive 9.8 meters per second squared. All right. So now, note, I have sort of two things. This is 8 centimeters. This is 9.8 meters per second squared. I'm going to need to use the same units throughout. So I'm going to go ahead and convert this 8 centimeters to 0.08 meters. I could, of course, also converted this gravitational constant to 980 centimeters per second squared, but either one works. Okay, so we can go ahead and move that to the other side. So we have 2 times 9.8 equals k times 0.08. We divide through k equals 2, 9.8 over 0.08. And that is going to simplify down to 2.45. Yeah. And if we have to attach units to this, it would be newtons per meter, or equivalently, kilograms per second squared. But I think newtons per meter is sort of the better way to think about this, because it's taking a distance and converting it to a force. Okay. So let's do our first example of actually solving one of these systems. So we have a 4 kilogram mass. Is attached to a spring. And it's stretching it 30 centimeters. The spring is stretched an additional 0.1 meters and released. All right, so we're going to solve this in two parts. First, we are going to set up an IVP, which models the situation. And then part B, we're going to actually solve the IVP. All right, so first we're going to have to solve for k. So again, we'll use, force due to gravity is equal to negative the spring force. Our mass is 4 kilograms, so we have 9.8 times 4 is equal to negative k times our displacement. 30 centimeters converted to meters is 0.3. So k is equal to 4 times 9.8 divided by 0.3. And just checking what that is, because I realize right now my key is wrong. We are going to end up with k equal to 392 thirds, or 130.33 repeating, or sorry, 0.6 repeating. Okay, we're now told we have our mass so 4 our mass times y double prime plus our k, 392 thirds, times y equals 0. Right, we're just using this formula right here, my double prime plus ky equals 0. We then have to account for our initial conditions. So we're stretched, stretching means we're going down, so an additional 0.1 meters, so y of 0 is 0.1. Y prime, so this word released is sort of another convention for these problems, and really what that means is that our starting velocity is 0. Right, so this would be our answer for part A. All right, then we want to solve the IVP to get a function for the spring's position. So let's go ahead and do that. We'll just 4r squared plus 392 thirds So going ahead and solving for that, we're going to get r is equal to plus or minus the square root of, well, let's see, 392 divided by 4 is going to be 98. And so we have square root of 98 over 3. And that should equivalently be, or sorry, negative that. So that should be plus or minus I times the square root of 98 thirds. This tells us, right, our general solution looks something like this. And now we want to go ahead and use our initial conditions to solve for this. So y of 0 is equal to 0.1. So C1 cosine of something times 0 is just 0, plus C2 sine of, again, 0 is equal to 0.1. Well, that vanishes, and we're left with C1 equals 0.1. For the derivative, y prime is equal to the square root of 98 thirds or times C1, negative that sign, and then plus square root of 98 thirds C2 cosine. If I plug in 0, right, sine of 0 is 0, so that's going to vanish. And cosine of 0 is 1, so we're going to be left with the square root of 98 thirds times C2 equals 0. So C2 equals 0, C1 equals 1/10, and so we can get our final answer, y is equal to 1/10 times the cosine of square root of 98 thirds times t. That is our final answer. All right, that should largely be enough for what you need for the web work, but I am going to say a couple more things. So amplitude, period, and phase. So let's say we've solved one of these equations and, we get something. I want to sort of emphasize, I would use C1 here, but I want to emphasize that we've actually found a value for our arbitrary constants. So I'm going to use A and B, and then we're going to use the Greek letter omega for whatever we multiplied by t. Okay. So we're going to sort of do a trick here. And really this trick just relies on the following formula. So if I do the sum of angles for cosine, this is my formula. So in particular, plus or minus becomes minus plus, so if I have a plus here, I get a minus. So in particular, if I do alpha minus b, or alpha minus beta, I get cosine of alpha times cosine of beta plus sine of alpha times sine of beta. And so what the trick is we take this, we rewrite y as the square root of a squared plus b squared times a over the square root of a squared plus b squared. So we're just sort of multiplying and dividing, times cosine of omega t and if we, because note that this squared, so if I square this, and I add b squared, then I get 1. So what that means is we can find some angle, say phi, with cosine of phi equals a over square root of a squared plus b squared, and sine of phi equals b over square root of a squared plus b squared. And in fact, we can do a formula for this. You can sort of check, but phi is going to be inverse tangent or arctangent of b over a. And that formula works, unless my a coefficient is less than or equal to 0. And if a is less than 0, then it's just going to be arctan of the same thing plus pi. If a is exactly equal 0, phi is going to be either pi over 2 or negative pi over 2, depending on if b is positive or negative. All right, so if we have that, then we get that a cosine of omega t plus b sine of omega t equals the square root of a squared plus b squared cosine of omega t minus phi. Okay, why is this important? Well, there's a couple things that are can be important to know in practice. So the first is what's known as sometimes the peak amplitude, but we're just going to call it the amplitude. And all this is in regards to y, our original function. So the peak amplitude is the max absolute value of y. So it's, what's y's highest point, it's going to end up being the same as the negative of its lowest point, but this is what we get. Well, using this formula right here, right, we can see we now have cosine of something, so that's always between 0 and 1, times this thing. So that tells us our formula for amplitude is the square root of a squared plus b squared. Our period is how long it takes y to repeat itself. So these are going to be a sum of a cosine and a sine. So, cosine repeats itself every 2 pi. It starts over, right? We can look at its graph. Starts here at 1. At pi over 2, we hit 0. At negative pi, or I'm sorry, at pi, well, and at negative pi, we hit negative 1. 3 pi over 2, and then 2 pi. We finally repeated itself, and then from there it just does the same thing. So the period is sort of this length. Similarly, amplitude is the height. And so if I have this omega here, if omega is 1, I'm going to have a period of 2 pi. Otherwise, my formula for period is going to be 2 pi over omega, right? So if I multiply it by 2, I'm going to repeat myself now every pi, because it's going to speed up the process. And then phase, a little bit more abstract in what it's defined, just sort of tells us where on the cosine we start, and that is phi, which we already had a formula for. All right, we'll just end it with an exercise. So a 2 kilogram mass is attached to a spring. Stretching it .5 meters. The spring is then stretched an additional 25 centimeters and thrown up with a velocity, or a speed, I guess, of 20 centimeters per second. So part A is just set up an IVP modeling the situation. B is solve the IVP and find the furthest the spring object ever gets from its rest position. So part A is straightforward. Part B, solve the IVP. Done that a bunch. Furthest it is from the rest position, well, that's really just asking for what's the amplitude. Okay, so pause it here if you want to try it. Otherwise, I'm just going to go straight into the answers. Not going to fully work these through, but I'll sort of sketch it. So here we should have two. If we convert everything into, this time I'll convert everything into centimeters. So we get 50 centimeters there. And then our G is going to be 980 centimeters then. So we have 2 times 980 equals K times 50. And we should get that K is equal to 39.2. Right, given that, it's pretty straightforward to set up the IVP. We have 2 for our mass times y double prime plus our K, 39.2 times y equals 0. Y of 0 equals 0.25, and y prime of 0 equals negative 0. Oh, wait, if I'm converting it to centimeters, it should be 25, and negative 20. That would be our answer for part A. part B, we should get as our general solution y equals c1 cosine of the square root of 19.6 times t plus c2 sine the square root of 19.6 times t. If we go ahead and solve the IVP, we should get that y is equal to 1/4 cosine of that plus, or rather actually minus 1/5 or 1/5 times the square root of 19.6. We're then asked, what's the furthest the object gets from its rest position, and we would do the amplitude would be the square root of that, or of that squared plus this squared. Oh, wait, never mind. My answer's wrong. Yeah, if we're doing everything in terms of centimeters, this should actually be 25, and this should be 20 over the square root of 19.6. So that'd be 25 squared plus 20 over 19.6 square root of that. Okay, so then these two parts would be our final answer. And I'll stop it there.